We thank the organizing secretary, convener, co-convener, and also the entire organizing team for organizing this nice event on material science and devices. And this is important. Yesterday, I was in almost in a similar conference, which was also in material science and devices. So it is very good that there are a lot of material science and device issues are coming. And here, actually, I'm going to talk about some work which we have done recently to develop some electron source. You can say miniaturized electron source, and which can be used in various applications. You can see a team here who was involved in this entire work. So this is our institute, IIT Delhi, and
Sir, your slides are not moving. You have to just click on the slide. We got stuck on the first slide only.
now
Yes,
is
sir.
it? Yeah. Okay.
Now
So
it is on second slide.
second slide. Yeah, I'm on the second slide now, and it is not in the slideshow mode. Whenever it is required, I will open the
Okay,
slideshow.
okay, sir.
Yeah. So this is our the oldest building at IIT Delhi, which also involves a library. And of course, now at IIT Delhi, if you happen to visit, you will see a lot of buildings, but still we managed to have some gardens, some flowers, and we invite all delegates in our institute. And we are always open for collaboration. There are a lot of collaboration which is going on in our lab and through our different facilities. So one state-of-the-art facility is nanoscale research facility at IIT Delhi. Those who are interested in nano materials or nanoscience and technology, one can look at this website and can use this facility and also can collaborate with the faculty members who are within this facility. The beautiful thing is that many departments of IIT Delhi, they are all involved, faculty members and students in this facility. So it is really a kind of interdisciplinary research which is going on in this facility. Another is our central research facility. And we have the campus in New Delhi, Hotchkiss, and we have another campus at Sonipat in Haryana. And this campus is basically made for to establish this central research facility. And this central research facility also is a program called Sathi, which is been approved by DST, and the equipments and other things have been installed. So this actually had a sort of interface between the users of different institutes of India and IIT Delhi. So one can use, there is a timeshare of the facilities which are there under Sathi. So one can use this facility for their research. And if you want to know more about this, you can go to the website, or if you just send me an email, I can connect this with the relevant person, and you can get the help from these facilities. So now coming back to my subject again, the electron source. So all of us know about electron source. We have seen from school level, we have started working with electron source. And whenever the electron source comes in our mind, we think that there is a small filament kind of thing which can be heated, and then electrons will come out from this filament. And during our college or university time, we were used to always use these particular equipments. That time labs used to be all these equipments, that old valve and all these things. Although recent students do not know about these equipments, they are mostly all are integrated and chips based. But that time it was very popular. So these electron sources were used in almost all these equipments. And whenever we talk about this electron emission, this is actually thermionic electron emission. We remember Professor Richardson and Professor Dushman, who gave theory in 1928 about this thermionic emission. One important thing is that this is hot electron source because you have to heat the filament in order to release electrons from this filament. Almost, I mean, in 1928 or 29, almost in the same time, two other professors, Professor Fowler and Professor Nordheim, gave a theory on cold electron emission. And they talked about that electron, that without heating a filament, electron can be emitted from the material. And the way they describe their theoretical model is that if you have any material, suppose you consider a metal. So in metal, you have electrons are filled up to Fermi level. And then if you apply little bit of bias, which is typically in diode geometry, you have an anode here, you have cathode here, apply certain bias, and then this under this the potential gets little bit of tilted, and then electrons close to the Fermi level can tunnel out from this sea of electron, and you get the electron. Okay. The advantage is that you don't have to heat these anything. It is completely cold emission of electrons. So a big burden on technology is reduced. But you know that after that also you'll see 60, 50, 60 years, people have not used this cold electron source. They have only used that hot electron source. And I'll come back to this point why people did not use this cold electron source or could not use that. But you know, in 2010, 2011, this field emission based electron source was in big news because Samsung started an activity to make a display device out of this electron. So what was their idea is that this is on the cathode, you can have large number of electron emitters, and on the anode, you can coat, you know, red, green, and blue, typical RGB structure in a display device. And when electrons are emitted from here, they strike these phosphors, and then it can generate light, and which can be patterned and give a display. And that time, Samsung people also visited IIT Delhi. I remember we started this activity that time, and there were a lot of discussion that can we make a display device something like this out of this field emission, cold field emission process. But unfortunately, you know, the work on LED and LCD, they were so much accelerated, and the entire market was captured by those display devices. And slowly, Samsung also did not proceed much further. Although he had made some display device, I will display imaging that I will come little later for some other purpose. But these days, people don't talk about field emission-based display device. However, in our day-to-day characterization technique, everywhere we use field emission devices. Be it electron microscope, this we can forget for some time, be it electron beam lithography, and a new, completely new device, completely new X-ray generation tube, where one can use this cold electron source, and then there is no heating requirement. And every time you remove the source, you add the chiller to make this source cold. All those problems are removed if you have a cold electron source. Okay, but these equipments or these devices, people routinely use this type of electron source. Now again, I come back to this question, what I told a little before, that why, when the theoretical development was done in 1930s, why in technology it had to wait long? Because technology always demands something from the material scientist. Okay, so that time technology, material research and was not that much developed that they can make a cold electron source, because there are certain technological challenges. Because when you make a field emission electron material, you need to consider high aspect ratio. What is the aspect ratio of this material? What is and maintain a high current density, low turn on field, low current fluctuation. That means how do you turn on your field emission electron device so that the current is registered, and the temporal stability should be high. For a long time, it has to be used. Because if you discuss with any operator of microscope, he or she will always tell, oh, I'm facing a lot of problem because I have to always change the source. It's become after some time, it becomes unstable. So it is important that we make a electron source with high stability. And of course, the dimension of the material should be low. This type of field electron sources cannot be made with bulk materials. So one has to really research on nanomaterial for this electron source, and that is why it took a long time. So in our laboratory, we had, started working on two types of materials to make a cold electron source. One type of material is embedded metal nanoparticle. That is what I will talk in the beginning, and we call them planar emitter, and then sharp emitter, which are hexaboride decorated and metal decorated multi-world CNTs. I will also show some other nanostructures for field emission. We had actually for this study developed completely indigenously set up in our laboratory. It is being fabricated by our students in collaboration with some company. And this is very highly precisional field emission setup. So we can do an IV measurement using this field emission. IV measurement means field emission current density versus the field which is applied um, across cathode and anode. We can also make an image of it. Okay, so I will come to these points, how one can get IV curve and make an image. So outline of my talk is that first I will discuss about the metal nanoparticles embedded in dielectric matrix, and we call it as a planar field emitter. And second part, I will discuss carbon nanotube based field emitters, which we call sharp field emitters. So let me start with planar field emitter, and these planar field emitter are basically metal nanoparticles embedded in dielectric matrix. And two researchers in our laboratory have completed their thesis, Dr. Devalaya Sarkar and Dr. Hardeep Kumar, and I will discuss about the highlights of their thesis work. So this is a setup which we have used. This is actually a setup which is at Inter-University Accelerator Center. We just had a talk from Dr. Indra from IUSC. So there is a target laboratory at IUSC where they have developed this particular atom beam sputtering unit, and which we do by this technique. We actually, sputtering is known to all of us, but atom beam sputtering, what is done, that a silica target where some metal foils are attached, both are sputtered together, and then they come down, and then there is a substrate here which is on a rotating holder, and which rotates so that you can deposit a uniform film. These are certain parameters which have been used in this deposition setup. So in our case, we have considered nickel as the metal and silica as the insulating matrix, and iron cobalt metal also we have chosen. And then this is a typical, this view of how when the metals are embedded on a silica matrix. So generally these nanoparticles of metals are spherical, and if you have to identify this nanoparticle and find the atomic concentration of this metal, one is to do an experiment like RBS, Rutherford backscattering. So you can see very clearly this is a signature of nickel in Rutherford backscattering. The full width of half maxima with certain simulation can give you the thickness of the layer. And then this is also, this feature shows that it is silica. So it is very pure nickel nanoparticles embedded on silica matrix. And then if you look at under transmission electron microscope, you can see very clearly the contrast. So there are silica matrix with black spots are basically nickel nanoparticle. One can also improve the size of this nanoparticle by annealing process. That is what we do regularly to anneal at 200 degrees centigrade, 400 degrees centigrade, etc. So you can see the size of the particle, which is quite small here, become relatively larger when we anneal these particles. But when we had started with these nanoparticles, this is what an idea which came from my research scholar at that time, Dr. Hardeep Kumar. He told that why don't we use this in your field emission device or field emission setup? And we used this, and we found this, yes, these show the field emission properties and quite stable because these are metal nanoparticles which are embedded in an insulating matrix. But the problem which we faced with this is that these particles being spherical, their aspect ratio is not very good. And therefore, the current density, even after annealing, was not very good, and it doesn't match with the requirement or the benchmarks which I have shown to make a field emission electron display device. So how to improve this? We are stuck up in this point, but before with this understanding that the as the aspect ratio of this is not good because the particles are all spherical. You can see this is a typical particle size and shape which is spherical. Can we change the shape of the particle? That was the first challenge in front of us. And of course, before we change the shape of the particle, we anneal this particle to make them a little larger. And then we got an idea because that time there are a lot of the scientific community at this ion material interaction. They were using Swift heavy ion, which was just discussed before my talk. They were using this Swift heavy ion to elongate the particle on the matrix. So that is possible. So we immediately adopted that idea, and we irradiated this particle with Swift heavy ion, and then the particle shape is completely changed. Okay, so now you can see after irradiation, there are particles, not all particles, some of the particles whose shape is completely changed. They become sort of elliptical. One can also make a very elongated particle that is also been shown in the literature. The first step was to understand why it can happen, because we have to go to a little bit of basic physics to understand why the particle uh, change their shape. So we used a model, or we tried to explain. It is based on a model which is a well-established model of ion material interaction that is called thermal spike model. So in this model, if you just look at, maybe I go to a slideshow mode. So you can see these two plots. I hope you can see this slide. So these are the two plots which basically shows the lattice temperature very locally in few nanometer dimension, which is basically a result of electron phonon coupling from excited electronic temperature to phonon. Okay, so when ion interacts, it first excites the electronic subsystem. Electronic subsystem goes to a very high temperature, then it is coupled with the lattice, and then you have phononic temperature rise, and that is also quite high. You can see the y-axis scale, almost 3000 Kelvin, 3500 Kelvin. Okay, and the dimension is very small. So this is a very unique kind of heating a material very locally within a nano dimension. But anyway, what happens that when this Swift heavy ion interacts with the material, let me just pick up one particular nanoparticle here. An ion passes through this particle. So what happened? That a spike is developed. That is what thermal spike. I show it in this theoretical model, the right-hand side. So you can see a thermal spike is developed locally, both on the nanoparticle and in the insulating matrix. Okay, and when this temperature of this spike becomes higher than the melting point of both the insulating matrix and the nanoparticle, both of them go to a molten phase, and they have to come back to equilibrium. And when they come back, they came with a deformed shape. That is, it takes an elongated shape. So this is what our understanding is on this. And of course, this type of observation was not done by, as I mentioned, by our group first. There is a review article just before that where people have shown this elongation of this nanoparticle, gold nanoparticle, in a matrix of gold silica. And they gave a model that you can see when this temperature of both gold particle and silica, they go to becomes more than the melting point, then one can have this situation where one gets the elongated uh, nanoparticle. Okay, so we just extended this particular idea and we have generalized it a little bit, and we have shown that there is certain size range for which the nanoparticle goes to completely evaporation phase, and they actually promote the growth of some other particle, and that is the reason where you have seen that there is growth of very big particle. And there is certain range of size for which the nanoparticles get melted and they deform their shape and become spherical. Okay, but however, our experimental finding little bit differed from the theoretical of the model, and therefore one is to also look at how the pressure dependent parameters work here, size dependent values, all these things, and get an accurate result. But this was a good and fair way of explaining the uh, shape change of the particle. And then after almost 4 5 years, 3 4 years later, we did this experiment, field emission experiment again with these shape engineered particles. And you can see this is a flat one, which was earlier for the spherical particle. And now if we increase the number of ions, that is fluence, ions per centimeter square, we can see up to certain, the fluence, the field emission current density becomes very high for because of this elongation. This is not only elongation, there are some other factors which I'll just come to this point. But this is true that at certain fluency, field emission current density becomes almost 300 times higher as compared to which was there in the field for the spherical nanoparticle. But if we go to higher fluence, the particles get fragmented and the field emission current density again comes down. Okay, more investigation we have done on this. Now in this time now we used iron cobalt nanoparticle and try to understand why field emission current density enhances for this spherical nanoparticle. So we did calculation based on density functional theory, and we have found that and also with the help of the experiment like ultraviolet photoelectron spectroscopy, we have found that the density of state near Fermi level enhances. That is a very important point. And as the particles are elongated, the tunneling width, I have shown you the tunneling before, the tunneling width reduces significantly. And in this case, we could able to see a 500 times enhancement in the current density, field emission current density. So we thought, okay, this is very good, and we can now go for making some devices. Okay, so our the undergraduate students are very good in making devices. They like it, and they immediately, two students joined in a project with me, and they came out with a small display device. So you can see how does it work. So this is simply same as this diode model. This is where all our nanocomposite films are coated, and then it is connected with the camera, which can take the photography when this anode is coated with phosphorant. You can see this spot. So let me show you this. I hope you are able to see the spots. These spots are nothing but when electrons are going and striking this phosphor, which is coated on anode. And then this image can be completely analyzed. And this analysis can give us all the field emission parameters. That is what also we have developed. And also we try to generate alphanumeric out of this. This is what the students wanted. And they could able to do something with an electronic processor. But of course, as I told you that on display device, we did not go much. So we stopped after this display imaging after this particular work. And another kind of field emitter which we worked extensively and still working and made a lot of device out of it are these sharp field emitter, which are basically based on carbon nanotube. And we had 3 research scholars who have contributed: Dr. Shrikant Mataka, Dr. Rajkumar Patra, and now we have senior research fellow, Mr. Gulshan Kumar, and these are some highlights of the research. But the question is why we have used carbon nanotube. The reason behind this is that now we get a material which is having very high aspect ratio. So that gives a very high field enhancement factor. Okay, it can also generate very high current density, 10 milliampere per centimeter square, which is a typical benchmark, and low threshold field. That means the field where you see an appreciable current density. It is having other good physical properties also, and they can be used as very good field emitter. So when we talk about a superior field emitter, we should always remember that it should have low turn-on field, low threshold field, high field emission current density, and low electric field. Okay, and then other things which are important, because electron emission is basically emission of from a material which where the electrons get energy more than the work function. So low work function material are always used, and they are promoted in the quantum mechanical tunneling. And the as I showed you, the Fermi level density of electron density of state should be higher. So this is another important issue, and there should be more emission signs. So all these things are required in a research before we go for device. So we have used a very simple technique to grow multi-walled carbon nanotube, and this is called thermal chemical vapor deposition technique, where xylene and fluoroperoxene mixture are used as a precursor, and then we have a little heating zone here, and then we can see entangled multi-walled carbon nanotube. So the idea was, as I told you, that one has to see the aspect ratio as well as the low work function. So multi-wall carbon nanotube as such are not low work function material. Their work function is close to 4.8 to 5 electron volt. So in order to make the surface coated with low work function material, we have coated hexaboride, cerium hexaboride and lanthanum hexaboride. Why hexaboride? We all know that hexaborides are technologically applied material for electron source. If you discuss with any electron microscope operator, they will tell that I use an hexaboride source. But what we thought that let us use hexaboride small nanostructure and coat or design our multi-wall carbon nanotube with hexaboride nanostructure. And immediately you can see the green one is the current density which is from a carbon nanotube. And as soon as you coat a hexaboride, the current density enhances many-fold. So there is a high enhancement of current density along with a very good temporal stability. And similar observation we have seen with lanthanum hexaboride also. Okay, we have very good lanthanum hexaboride nanostructured also, which are being coated on carbon nanotubes. So we have the current coming almost close to the 2 volt per micrometer, and we have very sharp emission of electron, which is really useful for device. Okay, this is one set of material. Another is, we thought that, okay, so far we have made this entangled nanotube or sort of, the nanotubes which are zigzag on the surface. Can you make vertically aligned nanotube on the same setup? So Shrikant actually did a lot of experiment in this, and he played with a lot of parameters. And fortunately, we found some parameter which promote the growth of vertically aligned nanotube. On the top, if you see, they look like entangled, but if you take a cross-sectional view, they are really vertically aligned. And when you use a vertically aligned nanotube, generally, carbon nanotube gives a current density of around 2 to 3 milliampere per centimeter square. But with vertically aligned carbon nanotube, we can immediately see there is a jump which is almost 9 milliampere per centimeter square, which is close to the benchmark only with vertically aligned carbon nanotube. Okay, then we thought that okay, so when we try to use it in a device, it is always better that we make some patterning on that. So one way of patterning is lithography. So we had not gone for lithography at the beginning. We had adopted a little different procedure. We just take a mesh, metallic mesh here, and then coat gold film on our substrate. So gold actually does not allow nanotubes to grow. So after that, if you grow nanotube here, then these areas where golds are there is no nanotube. Okay. So in one way, this is a patterned, carbon nanotube. And then we did field emission. So this is a typical image of this pattern. So you can see there are bundles of nanotubes which are being coated. on the substrate. And we also did a sort of console simulation where we have seen that local electric field is very high when you make such bundles, and that actually lead to a very high current density. So this is one particular pattern. This is another particular pattern. So here we have seen maximum almost close to 16 milliampere per centimeter square, 16.1 milliampere per centimeter square. This is amazing because this is even above the benchmark which is required for a field emission electron source. Here also it's slightly different pattern. We could see more than 12 milliampere per centimeter square. And then we also did imaging with this in order to understand that whether how these electrons are actually they generate the emission, uh, intensity on the phosphor. And we found that when we use this, patterned CNTs, they give very good imaging with very bright intensity because you need a bright electron source in that. One can map this image and see in the three dimension how they look like, the images. Of course, there is another mode, the material which people have already reported in some literature, that if you don't pattern, if you don't, use any other lithography, but want to increase the current density, one way to do it, just make some little bit of metallic nano dot on top of it. That is called metal decoration of carbon nanotube. That will lower the work function. It can increase the density of state near the Fermi level, and it can also create extra emission size. So we have done an experiment with this, and we have seen that this is one result where we have seen with coating with the India metal, the current density becomes close to 4.5 milliampere per centimeter square, which is little less as compared to patterned one. But after that, we coated many metals, which I am not showing, particularly with copper. When we coat, we see a current density of 15 milliampere per centimeter square, or close to 16 milliampere per centimeter square, which is almost same as the patterned one. So this is another material which can be used. And then this is one study which we have done to look at for other materials which can become a stable field emitter. In this case, we compromise with the current density, but this zinc oxide nanostructure can be a very good field emitter. And where low current density materials or field emission sources are required, one can use these materials. So now we have a project under device development scheme of Department of Science and Technology, where three institutes, IIT Delhi, TMU Moradabad, and INST Mohali, we work together, and we make various electron sources as material aspect is concerned for different current density ranges. So these are some materials which are relatively low current density. These are some materials which are intermediate current density, and these are some materials which gives high current density. And then we used all these materials in a source, electron source. So this is typically our setup. When we acquire the data, it is very high voltage, and this is the source, electron source, which have been designed and fabricated at IIT Delhi with some help of industry. And this is what you get to see when you acquire data, and this is a current source which can be delivered for the product. We are also planning to have, we already done it, to use lithography to make an integrated field emitter. The reason behind this is that you need some, so far whatever field emitter I have shown, they are all the chamber based. There are small chamber if you have seen. But without that, if you want to integrate, say, an electronic circuit, you need an electron source for that. One can use lithography. So there is a scheme which we have adopted that we can go a silicon substrate, SiO2, polysilicon SiO2, etch it properly, and then deposit after aluminum etching, and then finally you deposit vertically aligned carbon nanotube and get an integrated field emitter. And this is also under progress in DST device development scheme. Okay, so let me summarize now all the works which I have shown. So you can see these are all devices which are being fabricated and tested in our laboratory integrated field emitter, field emission imaging device, prototype field emission electron microscope source. And this is a setup which has been developed in our laboratory, prototype X-ray source. And X-ray we are testing this, and probably in some of my next talk, I should be able to show you the X-ray also. And these two types of material which we use, and as I discussed in my talk today, this highly enhanced field emission from shape engineered metal nanoparticle, vertically aligned CNTs, decorated CNTs, oxide and hexaboride nanostructure for all these field emission devices. Acknowledging the support from various funding agencies and institutes, we thank CSIR India for financial support, and that Germany for financial support, and also the Nanoscale Research Facility and Central Research Facility at IIT Delhi for research support, and Inter-University Accelerator Center New Delhi for various research support, along with the very good the high energy ion irradiation facility. Thank you for your kind attention, and Happy New Year to you all.